Hello all. Thank you for being here. We've heard some great talks. We just heard this talk on VLLM, which talks about a lot of inference, et cetera. And this is becoming an important thing. And as we look at AMD here today, and there's a lot of stuff that we're doing on these GPUs. So wanted to go over a little bit of that, give you a flavor of how we think about this. So first question is, why inference, right? We can, over time, we've been talking about training. There's these huge models that we're training that obviously use a lot of resources to train. But it turns out, once you've trained that, and what we're seeing is there are a lot of these common foundation models that you've heard a ton about. Some of those in open source, some proprietary, like the ones we've been using at Microsoft, for example, GPT-4o and so on. And there might be some, once you have those, a lot of these common models are used across a lot of things. You might have some fine tuning on top of it, but then once you have it, you might run this in production for a very, very long time. And so what we see is something more like this, right? If you think of this chart as, okay, you're spending a lot of resources on training for a while, and it keeps going, and maybe it takes a few months to train. But once you've actually trained it, once you have that model, now training's done, we start with inference, often start small, but grows. And the time that it takes, you'll keep running it perhaps even after the next new model is there, perhaps for a long time. And for some of these, overall, like the compute utilization for inference is actually very, very significant. So it's super important for us when we look at that area under that curve to focus on inference and really spend time optimizing that as well. Now, where does this show up? This is a chart which shows you, just looking at a couple of model families, the GPT-3 and GPT-4, and the variance that you see over time. Both these models started with a fairly high cost. GPT-3 wasn't too bad, $20. This is all this in roughly million tokens. How much does it cost? This is the output cost. The inputs are slightly different. But starting back there, we started to see it drop fairly regularly. And if you look at GPT-4, when it started, it was $60 per million tokens. But just in a year and a half, it's come down from there to less than a sixth of that cost. And all of this has been possible because we've been able to really tune the performance for this model in many different ways. There are model improvements, of course. There are algorithmic improvements. But a lot of that also comes down to what we can do with these amazing GPUs and so on. So when we think about inference, I guess, what are our goals, right? What do we want to do from a cloud perspective or from running these models perspective? It always comes down to performance, because performance leads to efficiency, better experience for the end user, leads to cheaper costs. The lower cost definitely helps us a lot in many, many different ways. But how do you think of performance? Is it just going fast? Is it something else? So the two key things that we look at is, of course, how fast can we go? And this is just speed of light in terms of, okay, I get a request. How fast can I respond to that? I would love for it to be as fast as possible from the user perspective. But the other piece that does matter as well is how much does it cost? So maybe I could actually do things super fast if I didn't care about the money. But that's not quite true, right? I do. So for example, there are vendors out there that talk about, oh, our system is so fast, we can get things down in milliseconds or whatever. I mean, yes, you put 1,000 GPUs for one request, you can probably do that. Is it going to be worthwhile for anything? Probably not. Most use cases, it won't make sense. So what is that sweet spot where we can provide both a great experience as well as great efficiency? Now, there are some, getting to this, there are constraints from experience perspective, from what people need. And most of that comes down to a couple of things, right? One, of course, low latency I talked about. And what's the driver for latency? If I'm running a batch job where I just need results on a whole bunch of data, it doesn't matter at all. It's all about just how fast can I go, like in terms of going through those. How efficiently can I go, rather, not even fast. But if I have a chat application where I'm talking to you or I'm talking to, I want an answer right then. If I'm running a search query or whatever, I want an answer right away. And so in this case, low latency really, really matters. But of course, the low latency itself, there's a dependency on the use cases as well. Now, I talked about the batch versus that, but even say a chat versus say summarizing a document or whatever, right? I'm looking at a doc, I have this Word doc in front of me, I'm asking Copilot to just summarize it, or maybe my Teams meeting and summarizing that. Then I'm going through a lot of content, whereas the chat, it's usually tiny bits of content generating and having that conversation, right? So it's very, very different. So first, let's talk about, when we talk about this latency itself, the question is, even that, as we start to go down, what does latency mean to us? Is it just that time it took for the whole thing? Turns out for many use cases, it's a little bit more complex than that, and let's just look at a couple of these. So, just breaking down a few of the key things that we talk about, and I'm sure, if you've been working in this area, you might have heard of many of these. First being, once we get a request, what's the time to the first token? This is, in large language model parlance, I guess. What does the time it takes to process the prompt itself or the pre-fill part itself, right? And this is often, can be more batched, et cetera. But then it's about, okay, if we are generating a whole bunch of tokens, if my response is going to be 1,000 tokens long, then how long does it take to generate all of them, or what's the average time between each of those tokens, right? So these are two key things that we measure because those define the experience that the user gets across those. Now, the goals for, again, the examples I was giving you earlier, the goals for each of the applications for these might be different. And in fact, it's just measuring these also is complex because you can measure it in many ways. The way we like to look at it is, often P95, which is what is the experience that the 95th percentile of the users are getting, because that's actually, when you look at across the board, that is what we start to see in terms of the experience of the users across, many different pieces. And as I mentioned earlier, there are different targets. So we might have a few milliseconds for, say, a chat kind of application where I really need to get that response right away. Whereas for others, it might be, it's fine if it takes, 100 milliseconds or 200 milliseconds or whatever, right? And so really optimizing for those, there are things that you have to look for and really get those. But now looking at these constraints, looking through these constraint size, at the end of the day, we do want throughput because that's what gives us the efficiency. The more we can run through, a lot of these GPUs are built for running through lots of data very, very rapidly. So the more we can parallelize, the more we can batch up together, the better we get. So, and the cost at the end of the day in the cloud depends on the throughput that we can get through those machines as well. So the goal here is how do we maximize throughput given those constraints, and really leverage those to get to the best performance per dollar in this case. Now, given that we run across many different kinds of hardware, we started with Nvidia, we've been deploying AMD now, the MI300s that we'll talk a little bit more about, and we have our own internal stuff as well. And so for each of those, there are different things to tune for. Some might be great for, say, doing those large batches of things. Others might be great for really responding very, very quickly to things, right? And how do we support all these different use cases, either on multiple hardware, or perhaps even the same hardware as well, right? It's super important to be flexible and be able to do that as well. So, this question is probably moot given that we are all here. Why AMD, I guess. But at the end of the day, look, we are making a choice every time we, purchase some hardware, every time we deploy, we are making a choice on why we want to pick that hardware. Sometimes it might be cost, sometimes it might be just what can I run quickly and so on. And there are a variety of things, right? And all of those matter. So one of those things for us, I guess, is that's always important to think about, and for many companies as well, is risk management too, right? As we think about these different things, yes, we care about cost, et cetera, but what helps us, not just in the short term and long term as well. having a plan B is always a good idea. And so we've been working with AMD for a long time. They've been great partners for us. And the way at the end of the day, we care about the cost each of these things adds up to. And the dollars do matter. And AMD has shown over time that the hardware that we've been building, that we've been working with, can give us that performance per dollar advantages and gains, et cetera, that we're looking for. And the third piece for us at Microsoft, of course, is our first-party hardware as well that we use for certain use cases too, and we combine it with the variety of options that we have. So now let's look at running on AMD itself. What does that take, and how did we think about doing this, right? In this case, it was a lot of work, and lots of folks in AI Frameworks team that I joined recently, and with tons and tons of help from AMD. So all the folks from AMD here, thank you for that support and partnership. That's been great. The way we think about it is there are a few different aspects of when you're trying to run a model on this hardware. And the first one for us and for many folks today, just where we are, comes to porting, because there are some models being trained on AMD itself, but then there are many others that might be trained on other hardware, right? On our friends over at Nvidia or other pieces as well. So the first bit is, okay, can we run that model easily here? And so let me just walk through some of the things that we went over that. It's interesting, some of this move is almost like, for the developers out here, it's like taking a program from one programming language, say C++, and going to Rust and trying to re-implement it or whatever, right? There are things that you learn, and there are things that you iterate with, and there are good ways of doing it, and there are things that are complex as well. So there are lots of things that need to be done here, and in fact, often, like with many things in life, everything that can go wrong does go wrong, but there's light at the end of the tunnel. Things do work. So I just talked about the broad thing there, right? And it does mean we need to understand both where we are running it today on whatever hardware it was running, and being able to run this on this new hardware. What are the nuances of each of those? How can we leverage both of those well? One piece that I would say goes to the heart of this as we made this change is really testing through everything. Now, if you think about the programming language analogy that I was making, the only way to make some of those changes is if we have a lot of tests that really compare the old one to the new one, and really make sure that things are comparable, right, where you're getting the same results on A and B. In this case, it turns out it's not always that easy, because if you think about, say, a program, typical program, et cetera, you get the exact same results. Turns out in math, especially fuzzy math, which we get down to in this case, things don't match bitwise. So you can't just say, oh, this is giving me A, and this is also going to give me A. Sadly, the answers are going to be slightly different. Is it not correct? Often they are correct. Once in a while, they're not correct, and you need to be able to differentiate that. So having a suite of tests at every possible level, right, all the way down to the core kernels as much as you can, all the way to the model, all those tests are super, super important and really save the day for us to make sure that we're getting the right things right. The next bit here is really thinking about one way to do it is, oh, I have this huge program, let me just rewrite it and then hope that it works, and if it doesn't, we'll just go through it. Turns out that doesn't work so well. Right? We have tried that, and now once you know there's a problem, it's very, very hard to figure out where the problem is. So one approach that often that has worked really, really well for us is if we can do things step by step, where you have this original model, and you take just a part of it and change that, and perhaps run it on the new hardware, in this case AMD. So in this case, perhaps kernel by kernel, if we can just swap out kernel one by one and run in both places. Perhaps we have a recording of the outputs of kernels from the old device and using those to plug in and run on the new device and slowly add functionality on the new side, those kind of things really make sense. And I like this picture because this sort of shows that, right? There's a gradation. We are making that change slowly rather than just going from that green to brown. That just does not work, right? That slow change and being able to test and validate that every single thing is working made a huge difference in what we were doing. And it turns out that the more steps you take, it actually goes faster rather than slower. So it's a weird one, but it's super important to think about that. Kernels, them specifically, they're like small functions. Yes, they might be complex, but they are more testable and easier to change. You can always start with an implementation that is not as performant, but just works, just provides that functionality, and that goes by really, really fast, right? It's possible to do that quickly. And that really helped us, right? Really breaking that down, going step by step. And we've learned through this process as well, right? Now, we've done it a couple times. We've gotten some things right and some things wrong. But with each process, we've been learning and we're working with folks to really make this better for the next folks that have to do it. One piece of advice, to invest in tools, make a huge difference. Right? Some of the pieces that I was talking about in terms of being able to compare those models, the more you can do it, the better. The more tooling you have to help with these processes, the better. And over time, we hope as an industry, we are, of course, building the abstraction layers. For example, we talked about VLLM, et cetera. Those are great. But as we move through some of these transitions, it's valuable to have these tools that we can all share and do more with. And we'll do our part to make some of that possible as well. So now once we have a model running, we had a model running on MI300. By the way, all of this work that I'm talking about is been, a lot of it was on our largest model. So in this case, most recently GPT-4o, that we went through that whole exercise. And it's running in production today on AMD machines, and you're doing great, extremely competitive. But once you have the model running, you still need to be kind of fast. If it's not fast enough, it's not going to add value overall, right? So it needs to be fast, and that needs a few different pieces as well, right? Once things are running, turns out because we have it running on another platform as well, at least, there often is lots of low-hanging fruit, and some of that comes from, oh yeah, there are these 2-3 kernels that we know that they are super slow because we've just made them work, and let's just optimize those, and the people who know how to do this can do it fairly quickly. Now, it's, of course, if you've written any of those kernels before, it's harder than writing a general C++ function or whatever. So but the people who know how to do it have done it really, really well. So I wouldn't claim to do it well, but there are folks on the team who are amazing at that. The next bit, and we saw a bit of that in some other presentations as well, is data types as well, right? So if you're, the first bit for making something run is use FP16, FP32, whatever makes sense, right? Or whatever variant is the easiest to run and easiest to get things going with. But if you can, get it down, cut down precision, et cetera, as well, that makes a big difference. So really tuning those basic things gave us the biggest wins. And it turns out, going from where we were, we very rapidly got that initial 2x, of course. The next step got a little harder, but still the next couple of weeks weren't too bad, where we got another 50%. And this is now at this point, we're talking about things that are already fairly fast. It would take a fair bit of work for anybody to get that kind of performance. But we were able to get these because they were like, again, as you start digging through code and what's happening, we ran into some data copy issues where you have some data on the CPU, you're trying to get to the GPU. Mostly there are standard ways of doing that, asynchronously, et cetera. Turns out there was one that was somehow synchronous, right? And sometimes figuring those out takes a while, but once you do, then getting some of those things is hard. This one, in fact, turned out to be a bug somewhere in the code, but again, great relationship. Great partnership. We got a lot of support and got some of those things fixed very rapidly. The next bit here was really thinking about different use cases as well. I mentioned different use cases, say summarization versus chat kind of thing. And as we started to look at what each of those needed, turned out for chat, there's a certain kind of thing because the latency becomes more important. There's a certain place points that we have to tune more for, perhaps lower batches, et cetera. And once we get those, it makes a big difference as well. But once you get to that, at that point, we probably have good performance that we could live with in some ways, and it's already running in production with good things. But now we need to just keep working at it. And this is no different than really running or getting performance anywhere. You measure how things are doing, figure out what's going wrong, where can we improve, et cetera, and you keep doing that. Really, the way I like to think about it is you really profile and iterate, and just the basic idea for performance always is right. Just the more you can measure, the more you can improve things, because unless you measure, you don't know where to focus on. We all have ideas, oh, this is the worst thing. But unless we measure it, we have no idea. So again, in this case, having great tools to measure and performance and benchmark and have clarity on that and being able to iterate on that really made a huge difference for us and continues to. So this was some of the pieces, and I can't go into all the details of what all happened in there, but this is how we went through this whole porting exercise for GPT 4.0, and then getting the performance and getting the performance dollars that we were talking about earlier. Now, is everything great for MI300? It's a good GPU. Like at the end of it, we love it, but everything has its issues as well. So let's talk about a couple of things that are harder. Look, it is a newer software stack, which during the process, we have found some issues, but we've been able to work through those. We've gotten the right level of support to be able to get those very, very rapidly, and things have worked really well. So we did hit some rough edges through this process. I think what worked great and what I see here, which really matters at the end of the day as an enterprise, is that there's just great support. When we have an issue, we have people who will help us, who know how to fix those things, who really care about these problems, and who want to make this great, right? And so what we've seen over this period, and we've been involved in this space with AMD for a while, and we've seen huge improvements and consistently and often, and we keep seeing that improvement, and it feels like a great thing for us to continue with. So I started with the cons. Let's talk about a few good things about it as well. And one, of course, for folks who've been playing with GPUs compared to, say, the A100 or H100s, this definitely has a lot more memory, and that does help us in a few things. Of course, higher memory bandwidth as well. And there are areas, that we are trying to, with these large models, trying to fit more, trying to squeeze more into those GPUs, and that helps us do some interesting things. One of the the most obvious ones is really helping with the extra KV caches in terms of just what we can do and how it helps the overall performance story as well. So that was really one of those things that helped us go beyond what we could do on some of the other things. There are more things that we continue to work on and iterate on, and I think we hope to see, given the value and the performance in the chip, we hope to get more as well. So this was in this case, I talked about an example where we had this model running on an Nvidia GPU with a lot of custom stuff, a lot of super optimized kernels, et cetera, et cetera. And we were still, we went through the story where there was a lot of effort put into both port and get to the performance, et cetera. And we saw that, yes, we could still do it. There were things that we had to go through, but it still worked pretty well. Let me tell you about a slightly different example where we went through a similar exercise, but that went through way faster. And we had this story talk about Triton earlier this morning. And in this case, we had a model where we had primarily started with writing a lot of the code and the kernels in Triton itself. And with those kernels, we could basically, the whole idea about Triton is, okay, we have this at a high level. It's not tied to the architecture of the GPU itself. We can compile it to different use cases or different things, et cetera, as well. And in this case, It took us just about 1 week to really go from the first platform to the second one to be able to get this running on MI300. It was super fast and with fairly good performance, right? So yes, it wasn't the super most efficient kernels to start with, but neither was it on the first one. And what mattered here was that time to market and things really made a difference, right? And in fact, we went to the similar performance and quality and everything in 2 to 3 weeks, right? So really, that's the kind of thing that we're looking for, and we continue to invest in to make sure that we do better on that. So overall, it's been a great journey with in this process going across some of these models. We are looking forward to continuing our partnership, and thank you. Go ahead.